Yes, thank you very much. Good afternoon, everyone. Thank you for the presentation. First of all, I would like to thank Peter and Kule for organizing this nice event. I think even if the workshop is still not finished, we can say that it is already a big success. Because I think what is important from researchers is to have contamination. And here we have seen people doing magnonics who are interested in three-dimensional system and vice versa. So I think this is already a good starting point for even for the future. So I work in Perugia at the National Research Council, Istituto Officina dei Materiali. National Research Council is the largest research institution that we have in Italy. There are already more or less 6,000 researchers working in all the possible research line, physics, chemistry, engineering, medicine, biology, and so on. So the physics department at the CNR is divided into 12 institutions. IOM is one of these 12 institutes, and the headquarters is in Trieste, where we manage several beam lines at the electrosynchrotron source, light source, and also in Grenoble and in Lund, where we are responsible from one end station at European Spallation Source. Perugia is here in the center of Italy. I'm leading the research unit there, and most of our activity is dedicated to use brilliant scattering spectroscopy, as we have already seen several times today, to study the dynamical properties of magnetic nanostructure in general, which means films, multilayers, patterned systems, and magnonic crystal, of course. We have already Sardinia. We have a theoretical research unit. It's not one day the Virgo new gravitational wave detector. So, but they are planning to build there. So you have already heard about this European project. Our BLS laboratory is now part of this network, which is a distributed network at the European level that combines synthesis, advanced characterization methods in ordinary laboratory and large-scale infrastructure. So the message is that we have built this very large consortium with 23 institutional partners coming from 16 countries, and we make available a large number of techniques, almost 200, in different places. So anyone could apply, submitting a proposal. You have, of course, to identify the technique that you want to use. So, and after the standard procedure of the evaluation of the proposal, you can get access and beam time, and you can come to our labs. So just to give you some idea, in the last 2 years, we hosted almost 10 experiments that were proposed by a researcher. Benjamin was one of them. Also, Hule was there. And so our lab is open not only to our own research, but we are also open to host other colleagues. So there is a list of people that I have to acknowledge. First of all, Adekule, because when I was presenting this talk, I was looking to my previous literature, and I found that I started work with him almost 20 years ago. It was a very fruitful collaboration, on both sides, I believe. We published something like 50 papers. The next one will be published in the next few days on Physical Review Letters. So it's on another topic, but I think that in research, you have always to have some people with who you have a very good relationship as a person, not only as a researcher. Then I have to acknowledge, of course, all the funding agency and so on. So my task is a little bit easier because we have seen a lot of things that I'm going to present. But first of all, I would like to give you some hint about what is the real motivation, why we need to go to three-dimensional magnonics. Because we have some problem that we are not able to solve in 2 dimensions. The simplest problem is that there's a spin wave that propagates over a planar film doesn't like to bend. It is almost impossible unless you use some trick to bend the spin wave beam. While in 3 dimensions, I will show you some example that it is very easy. So I will. The talk is divided mainly in 3 boxes. I will provide some example of what we call vertical magnonic crystal. As a matter of fact, we are not dealing with real three-dimensional lattice. but the message is that we want to have some layered structure to see how the topmost layer controls the propagation of the layer underneath. We have seen already in the Benjamin talk how the ASI island control the propagation and influence the propagation of the spin wave in the continuous film underneath. Then I will present you rather new research activity we started a couple of years ago that we call this twisted magnonics. And finally, I will show a couple of examples of some practical devices that can be used to vertically shift a spin wave beam from one plane to another one. So there is no need that I introduce the concept of magnonics. It has grown a lot during the last 10 years. We published roadmap articles. The first one was very successful. We are waiting for the second one that will be published in the next days. Andri also presented his roadmap on spin wave computing. There are several advantages of using magnonics with respect to the other technologies. And I think that magnonics can represent a bridge between classical or conventional electronics and photonics because it can push the technology toward the terahertz frequency range and to the nanoscale. As you can see in this graph, there are some overlapping with the other topics and other communities. And I think that here there is the space for us to grow, to exchange experience, and to make our research really interdisciplinary. Based on my previous experience on coordinating the roadmap, IOP asked me to coordinate the first roadmap on three-dimensional nanomagnetism that will be published in a few days. So in the end, I'm really happy of the result. We collected 18 papers from 40 experts, so I think this will be another step toward to increase the visibility of the research that we are doing. So some of the preliminary ideas of what we mean by three-dimensional magnonics were already identified some years ago, but at that stage, all the ideas were very, how to say, not well defined. What was clear for us is that we can take advantage of the three-dimensionality because we can add new kind or even stronger interaction between the layers. We can take advantage from the curvature of this three-dimensional object. We can create smaller devices which are less energy consuming. We can combine ferromagnets with other kind of system, ferroelectrics, insulating, antiferromagnets, and so on. And here you can see very schematic representation of the magnonic circuit that we have in mind. So it is made of different planes. Andri has shown just one plane of this circuit with all the different functionalities, and the box that you show here represent the different elements. You can have filters, amplifiers, spin wave antenna, circulator, diode, and so on. But what is important is that we should be able to connect the different layers. So we have to transfer the spin wave information from one layer to another one. Magnonic crystals are the starting point of our study. And what I want to say is that we are looking to the three-dimensional magnonics from the fundamental point of view because we think that if one is able to modulate the band structure or the frequency relation dispersion for the spin wave, one can gain a lot of information on the system. All the previous studies that we made in the last 15 years were made for planar system. Here you see some example. We are able to control the band structure, the opening of the band gap at the edge of the Brillouin zone. We are able to to guide the spin wave into narrow beams. What is still open is how to condensate the magnons into trap the magnets into very small regions. So you have already seen some example of spin magnetization dynamics in three-dimensional objects. These are just a couple of them. To see that there is now the mutual interest between people doing magnetization dynamics and people growing and fabricating such complex structures. Recently, we start entering into this game. Thanks to the collaboration with the Dennis Makarov group, we start to look to a sort of bicomponent antidot lattice. Here, the third dimension is given by if you look to the internal profile of the hole, you see that there is this parabolic shape with some cones and so on. What was interesting for us is that we were able to put in evidence strong anisotropy between the two different in plane direction. So as I said before, our starting point are the planar structures. So we have an array of elements made of two or more layers of ferromagnetic material separated by no magnetic spacer, or like in the case that's shown by Benjamin, we have an array of elements, in that case an AC system that is deposited on a continuous film. And we want to take advantage of the dipolar coupling. We know how this dipolar coupling between the different layers works. These are images taken from the original paper for Pritt and Grunberg, where using BLS he was able to quantify the magnitude of the dipolar coupling. And we also show that this functionality of the vertical magnonics can be changed by introducing a stronger coupling like the interlayer exchange coupling. I will show this in the case of the twisted magnonics system. So this is the first example of the vertical magnonics. This is an array of nanowires made by two different layers of permalloy with different thickness. Due to the different coercivity, we are able to stabilize either the parallel and anti-parallel configuration. And we measure the frequency dispersion by irregular scattering by sweeping the wave vector. And we see the presence of propagating mode, the blue one, and stationary mode at low frequency. And it is, what does it mean that the frequency is changing? Is that this array can behave like a filter. If you excite the system in this frequency range, the wave can propagate through the array. If you are out of this range, the spin wave doesn't propagate. In order to understand why we have this low frequency stationary mode that are different from the case of the single layer permalloy stripes, we have to calculate the spatial profile of the standing modes in the two layers, and only the mode that are oscillating in phase, the dynamical magnetization oscillating in phase, they are able to give rise to a propagative behavior through the lattice. This is another example. We have an array of ellipses on top of a continuous film. Even in this case, we can stabilize the anti-parallel configuration. But what is more important is that even if this dipolar coupling is a very weak interaction if compared to the interlayer exchange coupling, nevertheless, it is sufficiently strong to couple the dynamics of the continuous film underneath and the elliptical elements. And this is particularly visible in this region where the extended mode of the film, the mode M1, and the fundamental mode of the ellipsis, they interact. At some point, you see that there is here, close to the hybridization region, a strong imprinting of the mode profile from the ellipsis to the film. So in that region, they are strongly interacting. Then we study also another very interesting system that is a coffee bee film that is deposited on top of a pre-patterned silicon substrate with rectangular cross-section. We measure the band structures. We see that there are a lot of dispersive mode separated by band gaps. All the mode appears in couple, etc. But the fact that we see a continuous dispersion means that we have a spin wave beam that propagates following this meander shape of the film. So it means that even if there is a 90-degree angle, the spin wave is able to propagate. And this is because you see that the scattering geometry, when the spin wave propagates on the horizontal or vertical elements, the relative orientation with respect to the field doesn't change. We are always in the Demon-Eschbach configuration. You see that there is no band gap in the center. That is quite understandable because the system is is uniformly magnetized. And this meander-shaped film can be used as a waveguide to shift the signal from one level to another one. Because if you have one device here and one device there, the spin wave can transfer the information from one level to another one. We have also extended this kind of investigations to the case of two ferromagnets separated by tantalum, coffee bee, and permalloy. And this is the the structures, and the relation dispersion is slightly changed because we observe the presence of stationary modes that corresponds to the fact that we have out-of-phase oscillation in the vertical elements. That of twisted magnonics, the idea is not new. It derives, is well known in optics and in 2D materials. The idea is that when we have two lattices and you try to twist one with respect to the other one, you are introducing an additional periodicity that is the moire, that is called the moire superlattice. And if you consider graphene that is made by single layer of carbon atoms, when you twist one layer with respect to the other one, you reach a twisting angle where the density of states, the dispersion, the energy relation becomes flat. This means that the group velocity of the electrons goes to 0 and you have a very large density of states. So we have tried to replicate this concept. Of course, in the graphene we have atoms, but we are considering antidot lattice. So each hole, of course, the dimension is much larger. Each hole represents a carbon atom, and then we put one layer on top of the other one, and we simulate the relation dispersion. So when we have the two layers that are placed one on top of the other one, and they are just coupled by the dipolar interaction, nothing happens. Nothing strange happens with respect to the single layer. But as soon as you introduce the interlayer exchange coupling, we see that for particular twisting angle, there is the formation of a flat band. The flat band is formed at the center of the Brillouin zone, not at the edge, as usual. And we performed a systematic investigation of the line width of this flat band and found that the optimal condition is reached for a twisting angle that we call the magic angle of 3.5 degrees and an interlayer exchange coupling of 11 microjoule per square meter. And if you make a Fourier transform, for this particular value of the magic angle, we show that we are able, simply by twisting one antidot lattice with respect to the other one, to to concentrate the magnons into a very small region. This was just, and this has a strong analogy with what is made in photonics. And the people are now trying to use, they call this particular twisting angle where they have a large concentration of photons like the magic angle laser. So then we have tried to make experiments, but we had some problem because when we patterned the topmost antidot lattice, it was collapsed on the bottom one. So the Hanchen Wang, the former master students at the University of Beijing, came out with a very nice idea. You just take the two antidot lattice and just by computer you superimpose them with the proper twisting angle, and then imprint the resulting moire superlattice onto one single gig film. And here you can see a nice image of this moire superlattice. We map the intensity of the spin wave beam, over the spin waves that are excited by this coplanar waveguide by microfocus Brillouin scattering spectroscopy. And what it's the final results is that here you see the comparison between two spectra that are measured in two different points. The red spectrum and the red and blue spectrum are measured in different positions. And if we map the intensity of the spin waves, we see that these two modes have a very different character. The mode at 3.1 gigahertz is an edge mode that exists just close to the edges of the moire superlattice, while the mode at 2.9 is the cavity mode. So we have been able to concentrate, even if, of course, the size of the unit cell here is in the micrometer scale, we are able to concentrate the magnets in this, at the center of the unit cell of the moire superlattice, just simply by modifying the band structure. And we have verified that, of course, this critical angle depends on the applied field, and we have mapped the evolution of the magic angle as a function of the field and the twisting angle. Of course, to understand the properties of this localized edge mode, which propagates following this particular zigzag profile, we perform micromagnetic simulations. And the main message is that this edge mode that you can nicely hear, all appearing only for one particular angle, derives from the hybridization with the mini flat band that originates in the region where there is the band gap for the original antidot lattice, and this mini flat band mode is hybridized with the propagative mode with the positive group velocity. So I will start the last part. Fortunately, I will take advantage of the introduction that Andri have made before. The directional coupler is a very known system in integrated optics. You have two parallel waveguides, and the signal, in this case, spin waves, are transferred from one waveguide to the other one. And this transfer is efficient after that the spin waves have traveled over a particular length that is defined as the coupling length. Then we compare the results of micromagnetics with analytical theory. These are essentially the same. We use the same parameters that were contained in the original paper from Andri. So there was a perfect agreement between them. You have to consider that this separation between these two modes is a measure of the dynamical coupling between the nanowires. This configuration has some problem because, as I will show you later in the next slide, the coupling length increases a lot when you increase the frequency. But to overcome this problem, we have made this very simple change. We have put one waveguide on top of the other one. Andrei was saying that in this case we have a stronger interaction, and this is really the case. But we also found that there is a new feature when we have these two waveguides in the vertical configuration, and especially in the parallel, where the magnetization are parallel, is that there is the appearance of a crossing point. So at this point, the coupling is zero. So if we excite one waveguide at that frequency, the signal cannot go back and forth to the other one. And in terms of the practical realization and the utilization of the devices, as I told you before, in the planar configuration where the two waveguides are on the same plane, this coupling length increases a lot. While for the vertical configuration, with the magnetization either parallel or anti-parallel, it remains almost constant. So it means that we can create, in the vertical configuration, faster devices with smaller dimensions. And essentially, we don't need that the two waveguides are parallel over a longer distance, but it's sufficient that they are very close over a limited length. So this will also help us to reduce the energy consumption. So as take-home message, this configuration is preferred. So you can excite the system on one waveguide and detect the same spin wave beam on the other one, but the two are on two different levels. So this is another way that you can use the advantage of the three-dimensionality to switch, to shift a spin wave beam from one layer to another one. Here, this is the last example. It's a very simple system. Even in this case, we have tried to engineering the band structure or the relation dispersion of the spin waves. The system is made by two ferromagnetic films separated by no magnetic spacer, and on top of just one of them, we put an EV metal. So we take advantage of the interfacial Dialon-Chisky-Morier interaction. So as soon as you introduce that EV metal, you break the symmetry of the system, and you will see that there is a region for positive wave vector, for positive propagation. So the spin waves goes from the antenna to the right. There is a strong coupling between the two layers. Otherwise, if the propagation is in the negative direction, the coupling is very small. And you can realize a very simple device that we call the spin wave diode, in the sense that if the propagation of the spin waves is opposite to the direction where the coupling is strong, essentially this device doesn't do anything. So you excite the spin wave here, the input antenna, and you have just, due to the weak coupling, essentially no transfer of information to the topmost layer. But when you reverse the direction of the spin wave propagation, and it is in the same direction of the red arrow, you see that there is a significant transfer of energy from the bottom layer to the top layer. And here there is nothing. So this works as a diode, for example, but also enables to transfer the signal from one layer to the other one. This concept can be generalized. Here the situation is a little bit more complicated. We have still we had a topmost ferromagnetic film, even in contact, always in contact with the platinum in EV metal, and we realize a symmetrical situation. We have two films, and these stripes in between that we call the diode element. And depending on even in this case, on the relative orientation between the spin wave propagation and the coupling direction, we can realize in 3 dimensions a circulator. It's a system that permits to bend the spin wave beam passing from one layer to the other one. So in the first case, if you look to this movie, you are exciting, you have the input antenna on the top right part, and the spin wave propagate without significant transmission of the signal on the bottom layers. But if you reverse your system and the spin wave propagates parallel to the direction where you have a strong coupling, you see that at some point the part of the signal is transferred to the middle element, and it is reflected and then is transferred to the bottom layer. So here you have this, as shown by these green arrows, you have the circulator, microwave circulator on the nanoscale, because you know that all the microwave devices are bulky systems. They use millimeters, Higgs spheres of some millimeters in diameter, but here you are just using ultra-thin films. So this is the conclusion. I leave it just here. I hope that I convinced you that exploring the third dimension can provide you some additional degree of freedom to control the spin wave propagation on the nanoscale. I think that this topic of twisted magnonics that is just at the beginning will open path for the discovery of new physical phenomena. We are still working on this. I would like to announce, give the advertisement that we have an open position in Perugia for PhD student. So if you know someone who is interested in this topic, please contact me. I will just end this presentation with the announcement of the ICMFS conference. I will chair in Perugia the second week of July, together with one colleague, Francesca Casoli from CNR. This is a nice picture of the Perugia city center. It is a medieval city. It's a university city. You know, ICMFS is a very old conference. This year it celebrates 60 years from the first edition. So Italy will be the center of the research in magnetism. There will be ICM in Bologna, which is something like 300 kilometers north from Perugia. So we are exactly in the city center here, in a very nice place. So a lot of you, I know, will come to the conference. This is a plain view of the city. This is the fountain, the symbol of the city. The city was built 23 centuries ago by the Etruscans, who were the population living in Umbria and Tuscany. And Perugia is a nice city, but even if you move a little bit, few kilometers away, this is a nice picture of the city of Assisi, where I live, so I'm proud of this. So with this, I would like to thank you for your attention.